Hello and welcome to our short video introducing our EUSIPCO paper, which is entitled Real-Time Tracking of Multiple Acoustical Sources Utilizing Raoult-Blackwell-Lay's Particle Filtering. I'll begin with a brief summary of the intended applications of this work, which are mainly in regard to developing methods which allow a user to manipulate spatial sound scenes. This may either be done clinically in order to fix a problem with the spatial recording, or this can be done more creatively. Some examples include the ability to apply conventional single-channel effects on only certain sound sources in the scene. We're also interested in acoustical zooming and certain directional warping functions. And although we focus on the use of a single receiver in this current paper, provided that the tracking method is sufficiently general, extending it to multi-receiver 6 degrees of freedom type rendering should also be possible. Another potential application is to use the knowledge of the target directions in order to stabilize the rapidly changing directional arrival estimates which are used by parametric sound field reproduction methods. Therefore, to cover the intended applications, we employ the use of spherical microphone arrays since they capture the full 360-degree sound field. We then try to identify active sound sources in the sound scene so that we may consistently track their directions over time. We should then have all the information we require to start developing tools for the aforementioned applications. And ideally, we would like to have the option of doing all of this in real time. In a nutshell, the way we went about doing this was to first transform the spherical microphone array signals into the time frequency and spherical harmonic domains. We then employ a hard time frequency mask, which permits only the bins corresponding to a single dominant sound source to be let through. We then use eigenbeam esprit in order to obtain the directional arrival estimates, which we express as unit-length Cartesian vectors. We then feed these direction estimates to the tracker, which is based on the Raoult-Blackwell-Lay's Monte Carlo data association framework. And here it is. So the real-time system was implemented as a VST audio plugin. The directional arrival estimates are depicted as red dots on the graphical user interface, which plots them over time and separately for the azimuth and elevation. And for this particular recording, it looks like there are two active moving sound sources. And if we enable the tracker, we are able to see the trajectories of the two sources. Note that the tracker is able to adapt to time-varying number of sources since it evaluates the probabilities of new clusters birthing a new target, whereas stale clusters are eventually killed off. In the present example, as you can see, only one source is active at the beginning. The tracker then begins to follow the second cluster after it becomes active a second later and a new target is born. Additionally, since the tracker also models the velocity of targets, it is also able to follow moving sound sources, even if their trajectories cross over one another. To evaluate the developed system, we belatedly participated in the 2018 Locata Challenge, which involved localizing and tracking speech sources in a reverberant room and comparing the tracking results to ground truth positional data. We chose this evaluation approach since the challenge employed a 32-sensor spherical array, which was ideal for our system and comprised a few different scenarios of interest. We were then also able to compare our results to those of the original submissions to the challenge. And here are the results for the target direction error on the horizontal plane. The highlighted algorithms indicate the results for the original submissions to the challenge. Task 1 involved sound scenes that comprised only a single static source, while Task 2 involved multiple static sound sources. Task 3 then involved a single moving sound source, while Task 4 had multiple moving sound sources. As you can see, the results for the first two tasks are close to the winning submission, whereas the error values for the moving source tasks are lower than the original winning submissions. However, importantly, unlike the majority of the original submissions, our system was implemented as a real-time loop, and we also performed no post-processing of the tracker data. Okay, before I conclude this video, I'd like to briefly summarize some work that we've done since submitting the EUSIPCO paper. We've integrated the tracker into sound field modification tools, and this work has since been accepted at this year's DAFX conference. In this example, we have one plugin that first identifies and tracks sound sources and outputs their respective beamform signals. The user can then edit these source signals as they wish before returning them to the second plugin, which reconstructs the modified sound scene. Another, more recent project has been to employ the tracker in the context of multiple distributed spherical microphone arrays. In this case, rather than tracking sound sources from the perspective of one array, based on feeding the tracker unit vectors, we instead aim to track Cartesian coordinates in 3D space. And we look forward to sharing more about this project in the future. In the meantime, thank you for listening to this brief overview of our paper. Please join us in the poster session for more information or to ask questions or refer to the paper. Or you can reach me via email if you prefer.